Thank you, Patrick. It's really great to be back in Gothenburg and to be with all of you. This is my favorite time of year, conference season, when I get to get out and meet with other Mac admins and talk about work and what we do together. And I've been in this for a while, a long time. I started my career in 1993 managing a Mac lab and a Next lab at the University of California. And I wandered in the wilderness for a decade or so doing wireless telecom and network management systems and things like that. But I've been back focused on endpoint management for the last 10 or 15 years. And it has been really wonderful part of my career to come and attend events like this and to learn from other people and to meet people and get to know people. I've had the opportunity to do a lot of interesting things, and I've had a really nice career in this field, but it's all because of getting plugged into the community of people and the generosity of others that were willing to share with me and help me learn and help me grow up and learn how to do something useful. And so it really does mean a lot to me to come here to these events and to be with you. The last couple years, I've talked about my hobbies and tried to find a connection to what we do as Mac admins and things that interest me. So last year was Dungeons and Dragons, and the year before that was sailing. And I've recently gone into Formula One. And I think I am pretty focused on work. I think about what I do. I think about MDM and device management, all these things a lot. And so when I look out at the world, it's really hard for me not to look at just about anything I come across and not see a connection to what we do as admins. And so this year I started watching Drive to Survive. Oh, we've not got the sound. Let me double check my settings here because I do want you to hear a few things. Is this the right output? Can't see a signal. I think so. If we could just make sure the sound is set there. All right.
These guys have an almost fighter pilot mentality, and that's what separates them from mere mortals.
All I ever do is pray for a safe race. I never thought that I'd be there one day watching my son.
For me, it's heart attack after heart attack.
Are you okay, Nico?
Get me out, there's fire. There's fire.
I love the danger, that adrenaline and that excitement.
They have crashed! They've gone into each other!
I'll do anything I can to get the best results possible. I'm not worried about dying.
Really cool. I would recommend this series to you. So Formula One, if you've not been watching this along with me or follow racing, there's 10 teams or constructors in Formula One. And they each have 2 drivers. So there's 20 drivers in total, the very best in the world. Each team has 2 identical cars that they race. 24 Grand Prix every year in a season. And there's 2 trophies up for grabs, 2 championships, a team championship, the Constructors' Championship, and an individual driver's championship, which is awarded on scoring points and where you finish and all these different races that they have. The formula part is that there are a lot of rules around what you can do with your car. If you watch a race, you'll see immediately they all look very similar. You're familiar with Formula One, the open wheel design. They look very similar in part because it's a good way to design a car, but mostly because the rules say they have to look that way, right? And there's a lot of elements that, parameters, constraints that they have to operate within, and they're always trying to find little ways, little optimizations, things that they can do to make their car just that little bit faster. So among all the other things, there are thousands of engineers that work in this field and do lots of interesting things. This is an image of the piston head, right, that goes into a Formula One engine. And these piston heads are made of aluminum. The engine itself, it's one of those constraints. They have to be a certain size, a certain number of liters. They can only carry so much fuel on board. They don't refuel during a race, so they have to carry enough fuel to get through the whole race in the car. There's some constraints on, the cylinder size and liters and all of that. But these cylinder heads are really interesting. The piston crown is not flat. It's asymmetrical to fit with the valves that it interacts with. It's shaped in a certain way to direct the fuel to get the optimum combustion within the cylinder. It's manufactured to these extreme tolerances where the rings that they machine on the outside of the piston head, those are within like 2 microns tolerance, or 10 to 20, 0.01 millimeters. And they're actually forged. And so instead of taking like an aluminum or aluminium billet and machining the piston head out of it, they put it in a forge and they press it with a tool like this. And part of the reason they do that is so that the strands, the grain of the aluminum flows with the shape of the piston head, and it helps it retain a lot of strength while it's under stress. And of course, these engines have to endure a lot of stress. Not only, the 70 laps or so in a race, but the whole season. They go through a couple engines sometimes in a season. But all of this is combined together to make something really that's high performance. One other little oddity of that piston crown is it's not actually round. They manufacture them to be oval because when they're in the engine running at full speed, they deform to become round. And that gets a tighter tolerance within the cylinder. In some applications, they receive this diamond-like carbon coating, DLC, and they have to manufacture the piston head to be slightly smaller so that when they do the coating, it's exactly the size and shape that they want. Like I said, it's a bit oval, actually. It deforms to become round. The pin that goes through the head of the piston is also it has a bit of a curve to it because, again, when the piston shaft is moving up and down, it actually deforms under heat and stress to become straight. And they manufactured all of that in. This DLC coating that we see here, that was also seen on the Apple Watch 6 and the Space Black. If anyone had that version, same kind of material coating on the outside. This is the transmission, the gearbox in a Formula One car. And again, it's like 500 something moving parts in here. It's a 8-speed transmission, 8 forward gears and 1 reverse. One little detail, you can see the different gears in here. They're not stacked like 1, 2, 3, 4, 5, 6, 7, 8. They're actually set up so that the lower gears are on the outside of the shaft where they're closer to the bearing and they can handle more stress. And the higher gears are in the center where they have a little bit less stress from all the torque that you have in low gears. There's 2 shafts so that when you're in first gear, the other shaft, well, I'll explain this. The one shaft has all the odd gears, 1, 3, 5, and 7, and the other shaft has the even gears, 2, 4, 6, 8. And so when you're in first gear, the gearbox here can actually set up to switch to second gear on the other shaft so that you can switch from one gear to another in about 2 milliseconds. Okay? It's amazingly fast. But that's because they've engineered this really crazy gearbox. One other little oddity is the gearbox is actually like structural to the car, whereas in the road car that we all drive, there's a chassis and you bolt the engine into it and you bolt the transmission up underneath. In a Formula One car, the engine's connected to the gearbox and then the rest of the car is connected to the gearbox. So the rear wing, the axle for the rear wheels, all that is hooked up to that. Again, they're saving weight because they don't want to have a chassis that as an extra part. This is the differential. It works very similar to the one on your road car in situations where the differential is not under pressure. It works like a free differential. And when you're in a turn, right, the outer wheel has to go further than the inside wheel, so it has to turn faster than the inside wheel. The differential allows the wheels to spin at different speeds. But in a race car, that's not optimum because as you're accelerating out of a turn, because the car will be at a slight angle as it's cornering through a turn, the inside wheel might lose grip with the road and it'll just spin freely. So Formula One cars have a clutch on the differential. And so when there's pressure on the differential, the clutch will engage and add some extra resistance to the inside wheel to prevent it from spinning free and losing power that way. So all these tiny little optimizations, some of which are familiar to us from driving road cars, but in some ways, there's more advanced technology in the road cars we drive every day. And you think that would be strange, right? Why wouldn't they have the most advanced technology in Formula One? Well, for a lot of reasons, in certain cases, the rules say that you can't have the most advanced technology. You need to use what they've all agreed to use as part of the rules. But still, amazing engineering that goes into these road cars, the Formula One cars. So this is all the powertrain, the engine, the gearbox, the differential. Since 2014, Formula One has used a hybrid system where there is an internal combustion engine, a six-cylinder turbo, right? And there's also a battery-powered electric motor to assist. And the ratio is about 80-20. One of the rules that's changing in the coming season is the new rules will change that balance between the electric power system and the engine, and it'll be more like 50-50. And it's going to change the way that drivers have to think about strategy through the course and how they can use that power to overtake and maneuver along the track. Another really important component to all of this is aerodynamics, right? So the shape of the car provides a ton of downforce. It really works just like an airplane wing, but flipped upside down, right? The point of an airplane is to lift it up. The point of the shape of a Formula One car is to push it down on the ground so that the tires have good contact with the track, and you can apply that 1,000 horsepower that's available, about 750 or so in the engine and 200 or so in the electric motor, but 1,000 horsepower can be applied to the axle. Getting that force onto the ground is hard. So the idea is to create faster movement of air below the car, so low pressure, and the higher pressure air that's moving slower above the car will push it down. There's actually a Bernoulli effect that's intentional, so it creates little vortices underneath the car, and that creates additional downforce pressure. So the underside of the Red Bull car that won the championship 2 seasons ago had a really interesting, innovative design for the shape of the floor underneath the car to create those vertices, create that Bernoulli effect, and get some additional downforce. And that allowed them to be very fast. Max Verstappen, who drives for Red Bull, won the championship that year, and Red Bull won the Constructors' Cup as well. All right, these are the brakes. And this is the last thing I'll talk about with cars. But the brakes, as you can imagine, are even more important in a Formula One car than they are in your road car, because you're going 200 miles an hour, flat out down a straight, and you got to slow down to sometimes 35 miles an hour to get into a corner, right? So the disc here is made out of carbon fiber. And so the one on the left is what you see as the fabric, essentially, that carbon fiber is put together. And it goes through this process where they impregnate it, embed it with resin in an autoclave to bake it at temperature under pressure to get it to a really solid, rigid material. Then they machine that and drill holes in it for heat to escape. You can see those along the rim, the outer rim of the brake cylinder, and then the shape inside to engage with the rest of the mechanism. It takes them a couple months to make one of these brake pads because the carbon fiber has to be built into the disc. It needs to be baked for a week. Then they put it in a chamber with methane gas, which is, methane is CH4, carbon and hydrogen. And so through oxidation, you separate those, right? And the hydrogen goes out and all the carbon goes into the carbon fiber disc and fills in all the little holes and makes it even stronger than it was before. But that takes a couple weeks. It can take a few months to make one of these carbon fiber brakes. When they're under pressure, when they're in use, they heat up to 1,000 degrees Celsius. So that's the temperature of lava, right? And so heat management becomes really important as well. There's some interesting speculation about what McLaren is doing this year with their car design and how they're managing heat from the brakes to prevent that from going to the tires. But all this because as you approach a corner, you might be going 200 miles in the straight, and you need to slow down to, say, 35. If you start at 100 meters, right, versus an opponent who could hold and brake a little bit later and start that turn at 90 meters, that will result in about 1/10 of a second on that one turn. So you think about all the turns that there are in a course and how many laps you have to do, 1/10 of a second on every corner is a huge difference in a race that's decided by 1/10 of a second in the top places. Sometimes a few seconds, sometimes a bit more, but the range of finishing times is really close. And so they're looking for every little bit that they can get and spend a lot of time thinking about how to do this in the optimal way. So we have the drivers who are really incredible athletes, right? They are strong. They have to pay close attention they're in the car for a few hours for a race. They're driving for 90 minutes, maybe 2 hours. And as they're going through, they might be subjected to forces like 5G, 5 times gravity or more. Just for comparison, if you were to go to space in the space shuttle, right, the astronauts there are subjected to a measly 3G, right? Because they can control the acceleration here. But the Formula One, you've probably seen they have a special harness around their neck and pads and a tether on the back of their helmet, because as they're braking that hard, you can't keep your head up, right? So all that goes into this. The powertrain, the aerodynamics, the brakes, all of these components work together to make a really fast car. And the best teams are looking to optimize in every single area that they can find to create a winning car. So the team, though, is more than just the driver, right? There's the mechanics, there's the pit crew, engineers, there's logistics people, off-track, and trackside, strategy, making decisions about when to stop and when to change tires and all that. The technical director who oversees all the engineering, right? And the team principal who runs the thing. And there's also IT, right? So one of the things that's changed with Formula One over the last few years is there are sensors all over these cars, measuring temperature, speeds, tire pressure, the temperature of every component everywhere. There's cameras on it. And they're collecting all this telemetry from the cars in real time so that they can make better decisions around what to do. A lot of those are off-the-shelf components, the same kinds of sensors that you and I would use. CAN bus architecture that's used in automotive and other places. But one example of all these teams is the pit stop, right? And so here's Ferrari showing how it's done. Okay. It takes the whole team to win a race. And optimizing the pit stop to be under 2 seconds is a really important part of the overall performance of the team. So what does this have to do with Max Sisselman? Okay. A little bit, I think. I see lots of things in this that make me think about what we do. So I'm from Kandji, and we think about we don't think about, powertrain and aerodynamics and braking, but we do think about devices, security, and identity. Like the future is to bring all these things together so that they work well. Patrick had his good quotes. I found a good one to put up here. It's meant to be a joke, but it is true, right? If you're going to manage devices, you're going to secure them. If you want to secure devices, you have to manage them. These things are inextricably linked together. We do have the giveaway at our booth, so come by if you'd like to see more. But let me just show you a little bit of what we do. So we think a lot about how to optimize the experience for admins. So here's one small example. It's just something I picked. For File Vault, you decide if you want disk encryption on and if you want keys escrowed in MDM. You don't have to tell us what version of macOS or how we do it differently with key redirect or profiles or whatever. We just do the right thing for each version of macOS. We know what to do, so we just do it. If Apple ever changes the way File Vault works with DDM, right, we expect that this interface will never change, right? You just say, I want disk encryption on, I want keys to be escrowed. We automatically check if we have the key, the agent validates that it is fresh and it's signed with our public key, and then we have it. If we don't, we automatically retry and get the device to regenerate a key. If we have to prompt the user to log in, which is fixed in more recent versions of macOS or is done automatically in more recent versions of macOS, we will prompt the user with a nice little interaction to guide them through that so that we can make sure that the key is escrowed, because you took the time to check this box. We use a declarative approach where if you say you want keys escrowed, we're going to make sure that keys get escrowed. But we have all these other components in here as well. So certificates, controls, et cetera, they come together in a blueprint. So if we look at the map of all these controls that we've built, you can assign them into groups. So this first one here is for all devices. Everything will get these items. So we have some security controls, and this org uses Okta. But you've got some obvious choices like File Vault and Gatekeeper enabled here. But you can also assign apps to certain groups that come from the SCIM integration with your IDP and assign those things out. You can do an N-1 managed OS deployment where your early adopters get it right away. Everyone else that's already on Tahoe on version 26 will enforce the updates for Tahoe. If they're on Sequoia, we'll make sure that they continue to get updates for Sequoia. And if they're not yet on Sonoma, we'll make sure they get up to at least Sonoma. Actually, before I move away from that, I'll show one more thing. So when you're looking at this map, you can pick a specific device and ask to show the route that device will take through the map. So this is something innovative, I think, and something that we're really proud of, because not only can you see what is assigned to a device, but you can very quickly, easily see what's not assigned to a device and understand why that device is not getting those items. Something that could be invisible in other tools that I've used, we've made that visible to the admin. We've got EDR built in to detect threats and stop malware. And we also have vulnerability detection and response built in so that we have this catalog of auto apps, 200 plus auto apps. Even if you've not deployed that out to your fleet, if we find a version of an app that needs to be updated because there's a vulnerability in it, you can automate that whole process. We will automatically patch the apps that we find out on your fleet to the latest available version to try to address these issues. So what, again, does that have to do with F1? We think a lot about how to bring all these pieces together so that you can optimize the results. The good news is that we're not racing against each other, right? But we all get to work together as a team to get the best results for whatever it is we're trying to serve, right? Whether that's in education or in business or scientific research or whatever it happens to be. We're here, we're happy to be part of the community, we're rooting for everyone to win, but we know that it takes a team to do that. So thank you, and enjoy the rest of the show.